Good afternoon. In this video, we are going to talk about proposition 45 from book 1. I think this could be one of the most complex Euclidean construction propositions from book 1, but don't be afraid of it. Let's conquer it step by step, okay? So this proposition declares that if we are given a rectilineal figure and a rectilineal angle, then we are allowed to construct a parallelogram with the same area as this rectilineal figure and in this rectilineal angle, okay? So for convenience, let's just at first assume there are only 4 sides of this rectilineal figure, okay? And at the end of this video, I will expand it to multilateral figures, okay? So first of all, please recall the definition of a rectilineal figure. The boundary of rectilineal figures are different straight lines, which means we are able to divide it into different triangles, okay? So let us at first use postulate 1, and we join two opposite endpoints of this rectilineal figure to divide it into two different triangles, and let's assume they are triangle 1 T1 and triangle 2 T2, okay? And then please recall proposition 42. If we are given a specific triangle and a rectilineal angle, then we are able to construct a parallelogram in this angle and equal to this triangle, which means they have the same area, okay? So let's just at first construct this this parallelogram. So this parallelogram has the same area as T1 and it is in the angle A, okay? So we know that, let's assume it is B, C, D, E, and we call it parallelogram P1 for convenience, okay? So we know now we have parallelogram P1, right? And we know that angle EBC equals to angle A, let me rewrite it. We construct it the same as this triangle, so we know parallelogram P1 equals to triangle T1. Great. And then please recall proposition 44 we've just proved. If we are given these two conditions and a finite straight line, then we are able to construct a parallelogram equal to this given triangle in this rectilineal angle and on this straight line, okay? So let us use CD as a straight line we are given and T2 as a triangle and A as a rectilineal angle. So what we can do, we can construct another parallelogram with the same, with proposition 44. Let's construct it. Construct, let's say it is B, C, D, E, F, G. And so now we have, and for convenience, let's call it P2. So we have parallelogram P2 is equal to triangle T2. Besides, we construct it with a given rectilineal angle. So let's say angle DCF equals to angle A, okay? So they are two parallelograms we have constructed, and let's go to give the proposition a proof. So let me see, first of all, given these two conditions, and if we apply combination 1, things equal to the same are equal, we can imply that angle EBC equals to angle DCF, right? And if we add angle DCB to both sides, for example, we call it alpha, and apply combination 2, for example, things are equal, then if we add the same thing, the equality still holds, right? So let us add alpha to both sides. Then we have angle EBC plus alpha will be equal to angle DCF plus alpha, right? And since we know P1 is a parallelogram, so BE must be parallel to CD, right? And please recall proposition 29. If two straight lines are parallel and a straight line is cutting them, then the sum of two interior angles will be equal to two right angles, right? So they are parallel. So we know that angle B plus alpha will be equal to two right angles, correct? And if we combine them together and apply combination 1 again, see the left sides are equal, so the right sides must be equal. So we can imply that angle DCF plus alpha will be equal to two right angles, correct? And then please recall proposition 14, okay? So if we are given a straight line and a point on it, and there are two other straight lines on different sides of this straight line, let's say this straight line and this straight line, and if the sum of the adjacent angles are equal to two right angles, then these two straight lines are in the same straight line. Okay, so what do we have found? CD is a given straight line, and C is a point, and BC, CF are in two different sides of this CD straight line, and the sum of these two angles are two right angles, which means BC and CF are in the same straight line, okay? So let's say BCF, probably we can write this like that. So these 3 points are in the same straight line, okay? Great. And in the next step, let's go to these 3 different points to see whether they are still in the same straight line, okay? So let's apply proposition 29 again. So in these two parallel lines, alpha will be equal to alpha prime because they are alternate angles, right? So given that BCF is in the same straight line, we can say that BF is parallel to ED, right? Because we know that BC is parallel to ED. This is a parallelogram, and they are in the same straight line. So BF will be parallel to ED, right? And have a look at these two angles. Angle DCF and angle EDC, they are two alternate angles inside these two parallel lines, right? So we have angle DCF equals to angle EDC, right? They are they are equal, and let's call this angle beta. And if we add beta to both sides of this equality, the equality still holds, right? Because of combination 2 again. So we know that angle DCF plus beta will be equal to angle EDC plus beta, right? And what is angle DCF plus beta? Since these two straight lines, CF is parallel to DG, right? It's parallel, P2 is parallel, so CF must be parallel to DG. And if we apply proposition 29 again, we know that angle DCF plus beta will be equal to two right angles because they are a pair of interior angles in these parallel lines, right? So if we combine them together what do we know? So this equals to this, and it also equals to two right angles, right? And if we apply combination 1 again, we can imply that angle EDC plus beta will be equal to two right angles, correct? So EDC here plus beta will be equal to two right angles. And let's apply proposition 14 again. So if the adjacent angles, the sum of them are two right angles, then these two straight lines are actually in the same straight line. So CD is a given straight line, D is given point, and DG are two straight lines, and the adjacent angle, the sum of them are two right angles, and they are in the different sides of this straight line. So we know that they are in the same straight line. So let's write it like EDG in the same straight line. Okay? Oh, great. So now we have these two conclusions, which means EFGD is a, now we can say this is quadrilateral, right? So because these 3 points are in the same line, and these 3 points are also in the same line, okay? And then let's prove it is parallelogram, okay? So in the second stage, let's try to prove it is a parallelogram. So currently we know that with these two conditions, we know that BFGE is a quadrilateral, right? In order to prove it, let's pay attention to proposition 34, please. So the opposite sides of a parallelogram will be equal. So what? We know that these P1, P2 are two parallelograms, so we have, let's write it here, BE equals to CD, right? Because of P1, parallelogram. And we also know CD equals to FG, right? Apply combination 1 again, we know BE is equal to FG, correct? And besides, we know that BE is parallel to CD, and CD is parallel to FG, correct? And if we combine them together and apply proposition 30, we know that it declares straight lines that are parallel to the same straight line are parallel themselves. So we know that this is parallel to this, and FG also parallel to this. So these two are parallel to each other. So we know BE is parallel to FG, correct? So combine them together, we know that BE is parallel and equal to FG. Great. And now please consider proposition 33. If two straight lines, for example AB, are equal and parallel, and then if we connecting the extremities of them from the same direction, remember it must be the same direction, like C and D, it cannot be constructed like these. So they are not in the same direction. So these two extremities are in the same direction, and these two extremities are in the same direction. So we construct them like C and D. C and D must be equal and parallel. So what do we know? They are equal and parallel. And EG, BF are two straight lines connecting extremities BF and extremities EG respectively. Remember, we have proved these and these are in the same straight line, and also BC and CF. So this is a straight line, okay? So we know that BF is also equal and parallel to EG. That's great. And if we combine these two conditions together, we can imply that BFGE is not only quadrilateral, but it is also a parallelogram. Okay, that's great. And let me check. Okay, sorry, I forgot to prove the area. So we know that P1 parallelogram P1 equals triangle T1, and P2 equals to triangle T2. So if we apply common notion 2, we know that, let's say, triangle P1 plus, parallelogram P2 will be equal to triangle T1 plus triangle T2. And what is T1 plus T2? We know that T1 plus T2 triangle will be equal to the area of this quadrilateral, right? So let's say it as S. Assume this is S. So if let's just apply combination 1 again. Combine these two equalities, we can imply that they are equal, they are the same thing, so they must be equal. So P1 plus P2 will be equal to S, right? And what is P1 plus P2? It is the whole parallelogram, EBFG, right? So it is, so we can, if we imply combination 1 again, we can conclude that parallelogram BFGE will be equal to S, which is the multilateral figure we are given. That's great. So what? We have constructed the parallelogram BFGE, which has the same area as the given multilateral figure, and it is in the given rectilineal angle, right? Still remember this is equal to angle A because we constructed it based on proposition 42, right? So EBFG is a parallelogram we are looking for in this proposition, and it proves the proposition is true. Okay. So I would like to talk about this is a convenient or simplified situation because the proposition says that it is multilateral figure rather than a quadrilateral figure. Okay. So let's say if it's multilateral, for example, it has let me write it here. For example, it has 5 sides, and then with the same method we can at first let's say 1, 2, 3, 4, 5. It has 5 sides right now, right? And with the same method we can divide it into 3 triangles, and let's assume this triangle 3. Okay, so with exactly the same steps we are able to construct BFGE as we talked about in the whole proof method. So let's say BFGE will be equal to T1 plus T2, right? And let us just apply proposition 44 again so that we are able to construct another parallelogram here. For example, let's say it is P3. Okay, so that this angle is equal to angle A, and the area will be equal to T3, right? And FG is a given straight line as in proposition 44. And with the same method we can prove, let's call it EFGHI. With the same method we can prove that parallelogram BHIE has the same area as S. Now it has 5 sides, okay? It is this multilateral figure, and it is in angle A. great. And if we have more than 5 sides, we can just reproduce parallelograms in the right side again, and construct a whole parallelogram as we are looking for, or we are supposed to construct. Okay, that's great. So this is the end of the video, and in the next one we are going to talk about proposition 46, which I believe is the last Euclidean construction proposition from book 1. Okay, thanks for watching. Have a good day.